How about now? Okay, how's the audio now? Is it better? Hello? Okay, should be working now. Excellent. Kiblathan, can you hear me now? Okay, excellent. Let's do a quick video and audio check. Can you all see this clipboard? Excellent. And can you, if I move this file, can you see these notes in the background, which are now should be in the foreground? Are you able to read them properly? Okay. Excellent. Any questions, queries before I begin? By the way, if you want these notes, I've already uploaded them to the Google Drive folder, so they should be there. Okay, so no queries then. Let's just begin the lecture. Link for Drive. So when will we get the assignment? You will. I had to make some modifications to the assignment, so it should be, I've sent it back to the TA, so I should get it tonight, and you should get it tonight as well, hopefully. Jafar, the link for the Drive folder is the same, but if you want, you can go to Piazza and check, but I don't want to post it here. Let me just put it on Piazza. If you go to the master post on Piazza, it should be there at the end of the master post. There's a link to the Google Drive folder. It's already there, Jafar. If you check the master post, at the end of it is the link to the Google Drive folder, which should take you. The notes are lecture 3.3 Complexity of Algorithms. Okay, so let's just begin. So we've so far talked about the big O notation and the big omega notation and the big theta notation. The reason we talked in detail about these notations were we wanted to quantify the growth and the computational complexity of the algorithms. And this is where finally we're going to be using those notations. So far we were only just discussing the technicalities and the mathematics behind it, but now we're going to use it to discuss the complexity of different algorithms. And so the question first to address is, what is complexity? And complexity is directly related to the question of how do you measure the efficiency of an algorithm, right? So, and you can do that in different ways. The first thing that you can do is, of course, talk about the time it takes for your algorithm to finish. How long does it take for any algorithm to finish? That's called the time complexity of the algorithm. You can also talk about how much space and how much memory your algorithm requires. So if you're running the search algorithm or the sort algorithm, how many variables do you need to store in your memory? Of course, you will need to store the list in your memory. Maybe you need to store some copies of the list. Maybe you need to save some extra variables like I, J, M, whatever. So how much memory does your algorithm require? That's called the space complexity of the algorithm. Space complexity is something that we will not discuss in detail. It's something that you talk about when you have a better understanding of data structures. So, but I'll just still mention some of the ways that you can discuss space complexity. So if you know different data structures such as stacks or heaps or linked lists, these are different data structures which require different amount of memory to store them and which require different amount of memory to traverse through them. And so space complexity is directly linked with the kind of data structure that you're using. That's something that we're not going to discuss in the course. What we are interested in the course is the time complexity of the algorithm. So we're mostly going to talk about how long does it take for your algorithm to complete its task. And we're going to look at specific algorithms and talk about the time. The one thing that I want you to understand is that when we talk about the time, we're not going to be talking about the exact number of minutes or seconds that it takes for your computation to happen. Instead of time, we're going to be using number of operations. So maybe we can be looking at the number of floating point operations, or maybe we could be looking at the number of, is this in focus? I think it's a bit out of focus. Let me try to focus this. Okay, this seems better. So we either look at floating point operations, or perhaps we could look at the number of comparisons that we're doing. The reason we do this is because different computers have different speeds, and so if you have a normal laptop, then it would be slow in doing a floating point operation or a comparison. If you have a phone that you're using, then it would be even probably slower, but depending on these specifications of your phone. If you're doing it on a supercomputer, these operations could be quite fast. So instead of noting how many minutes or how many seconds it takes for the algorithm, we just talk about the number of steps it's going to take, so that you have a uniform discussion between different computer models, and you can account for the different time it takes. So of course, if it's a good fast algorithm, it would be even faster on a supercomputer. But we're not talking about those differences in computational speeds and processing speeds right now. What we're interested in is just how many number of steps it takes for different algorithms to complete their task. Okay, so that's something to consider. Now let's talk about a specific algorithm and how it does its task. So the first algorithm that we did in the course was, of course, the maximum element algorithm, which was, of course, used to find the maximum element in a list. You go through a list, you see which element is the largest, you set up Danya will talk about floating point operations and comparisons. Comparisons is simply saying whether If you're comparing two elements, you're just checking which one is bigger. And floating point operations are simply additions and multiplications and subtractions that a computer does. Okay, so coming back to the maximum element, what we're looking at is comparisons. How many comparisons do we need to make? So as far as the maximum element algorithm is concerned, let's consider what's happening in different steps. So firstly, it sets the maximum element to A1. Then it enters this loop for I equals to 2 to n. And it executes the steps. It checks whether your maximum is smaller than the current element. If it is smaller than the current element, then you change the maximum to that element, right? When we're talking about this algorithm, we're not going to be talking about this operation when you're storing something. We're only going to talk about the number of comparisons, because these operations are not as many as the number of comparisons. So the first thing that we're going to do is just limit our conversation to the number of comparisons in algorithm 1. And so let's suppose you have different elements. Let me just bring up the algorithm. What's important to note is that there are two different kinds of comparisons that are happening. The first comparison that is happening is implicit in this for statement, for I equals to 2 to n. When you enter this loop, I is set to, let's suppose, 2, but every time it is set, it's being checked whether it's less than or equals to n. So there is a comparison being made here every time you enter this loop. For example, let's suppose you executed this line and then you went back to the for loop. Your for loop is going to compare your element, your current I, it's going to increment I, and it's going to compare whether it's still in this range or not. So one comparison is already happening here, okay? And another comparison is happening when you're checking this max is less than AI. So in each step of this for loop, you're doing two comparisons. One to check whether your I is in this range, and two to check whether your maximum is less than or equals to AI. All right. And so let's check out what's happening. For the first element, you're not doing any comparison because you're just setting the first element to be the max. So there is no comparison for the first element. So 0 comparisons for the first element. For the rest of the elements 2 to n, you're doing two comparisons each. First, you're comparing whether your I is in this range, and second, you're comparing whether your max is less than or equals to AI. So there are two operations per each step of this loop, and the total number of steps is from 2 to n, which is n minus 1. So the total number of comparisons that are happening inside this loop are 2 times n minus 1. And lastly, when you've incremented, when your I is equals to n and you go back to this for loop, you will increment your I and I will become n plus 1. You will be doing one more comparison to check that I has exceeded this range. So to exit the loop, you need to do one extra comparison. And so the total number of comparisons is 0 plus 2 times n minus 1 plus 1, which is 2 times n plus 1. Does that make sense? And so because this is a linear function, it's 2 times n plus 1, the complexity of this function is of course theta of n, because it's a linear function. So we say that the time complexity of this algorithm is theta n. Okay, about the exit loop, let's talk about the exit case in some depth. So about the exit loop, let's consider you were doing I equals to 2 to n for I, and you were doing something over here. So what happens is you set your I to be 2, and then I becomes 3, and then 4, and let's suppose I becomes n. To exit the loop, what's actually happening in the memory is when you increment, when you go back after I was equals to n, you go back to this for loop, I is incremented to n plus 1, and then I is checked in this range. Is I still between 2 to n? It's not, it's compared, and it's seen that I has exceeded this range, and therefore for the exit loop you still need to make a comparison to exit it. So there is one extra comparison for exiting the loop. The second thing you asked was, why are we saying theta? We are saying theta because we can show that 2n plus 1 is big O of n, and you can also show that 2n plus 1 is big omega of n. You can show both of these things. A linear function is both big O of n and big omega of n, and therefore it is simply written as big theta of n. And the mathematical details, you can go back to the previous lecture and see how you can show that 2n plus 1 is big O of n and 2n plus 1 is big omega of n. Okay, about using omega, O and theta, the reason we're using is this function is a very simple function. For example, if you have a linear function, you can easily prove that it's bounded above by linear function and bounded below by linear function. For example, I can simply show that 2n plus 1 is less than and equals to 3n. For some, let's check for n equals to 1, this is 3 and this is 3. And so if I put n greater than 2, I will know that 2n plus 1 is less than and equals to 3n. So 2 times 2 is 4, 4 plus 1 is 5, 5 is less than equal. So I have shown that 2n plus 1 is less than and equals to c times n for n greater than k. K is 2 and c is 3. This is to show that 2n plus 1 is big O of n. The second thing you can do is for using the function showing it that 2n plus 1 to show that it is big omega of n. You need to show that it is bigger than equals to some c times n for n greater than k. Again, you can simply use 2n plus 1 is simply bigger than and equals to 2n, and you can do it for n bigger than 1, and therefore 2n plus 1 is big omega of n. And combining these two facts, you get 2n plus 1 is big theta of n. For the mathematics of this, just follow the definition. When I say something is big theta of n, I am basically saying that it is upper bounded by linear functions and lower bounded by linear functions. The details of it can be worked out, but we're not working them out. Okay? For simple functions, it's just easy to remember that if it's a linear function, it's going to be theta n. You can take n equals to 0. It would work for n equals 0 as well. Okay, is this clear? Any confusion? Yeah, sure, you can check n equals to 0. For 2n plus 1 greater than 2n, it will work for 0 as well. Okay. So let's move on to the next algorithm. Let's talk about the linear search algorithm. What does the linear search algorithm do? It looks at this list from A1 to AN and it's trying to find this element X in this list. We went through this algorithm in the previous lectures. So again, we're not going to be worried about the steps in which we're doing some assignment. We're only concerned about the comparisons that are happening. And so there are three different comparisons happening in this algorithm. The first comparison is of course very obvious to see, is I is less than n equals to n. We're checking whether I is less than n for each step. The second thing that we're doing is we're comparing whether x is the same as the ith element of the list. We do this to see whether we found the element or not. If we found the element, then we take it. If we've not, then whatever. Then we keep continuing in this loop. Then this is just an assignment, so we ignore it. And then in this step, this happens outside the loop and it happens once, is we compare whether I is less than n equals to n again or not. So three different comparisons happening. I less than or equals to n, x is not equals to ai, and I less than or equal to n. And the question is, how many times is this, are these comparisons happening? So let's talk about the first comparison, I less than or equals to n. This happens n plus 1 times. The reason is you set I equals to 1 first, and so it checks it first when I is equals to 1, when I equals to 2, I equals to, up until n it checks it. And an extra time that this happens is when you're exiting the loop. When you go back to seeing when I is n plus 1, this happens one extra time when you exit the loop. So this first comparison happens n plus 1 times. Second, you're checking whether the ith element is the same as the x element. This happens n times because this is not checked when you're exiting the loop. When you're exiting the loop, this condition already fails, so you don't check this at all. Because this is an AND operator, an AND operator needs both of them to be true. As soon as this is false, you don't need to check this. And so we check this only n times. And finally, outside the loop, this comparison happens only once. So you have n plus 1, then n, then 1, and you add them up and you get a 2n plus 2 comparisons in total, which is again a time complexity of theta n, which is a linear time complexity. Notice the words worst case written over here. It's written worst case because it's possible that you find the element x within the list somewhere. So for example, if the third element is the one that you're looking for, you will exit this loop immediately. This n plus 1 and n happens only in the cases when your x is the last element or it's not even in the list. So we're talking about the worst case when the element that you're looking for is at the end of the list or it's not even in the list. And so in that case, you get 2n plus 2 comparisons. Otherwise, you can get fewer comparisons as well. But in the worst case, you get theta n comparisons. If condition, this condition happens only once because of course this is outside the loop. So if I is less than, once you've gone through this loop, you just check whether I was less than n equals to n or not. If you want the details of this, you can go through the linear search algorithm and see how it's working. Okay. And so even this algorithm has a worst case complexity of theta n. It's a linear algorithm. Clear? Should I move on? Constant time, which steps do you mean? Constant time steps? No, theta is not being multiplied by n. This is the big theta notation that we talked about in the last class. Theta of n means it's lower bounded and upper bounded by linear functions. Hamad, I don't understand your question. No, we're not talking about assignments and additions. We're just looking at the number of comparisons. If you do want to add your number of additions in this, you can do that. And it's very simple to see that in every step you're doing, if you do this n times, then this step is done n times. So you will have another factor of n. So instead of 2n plus 2, it will become 3n plus 2. But even then, it's just theta n because it's still a linear algorithm. 3n, 4n doesn't matter. The constant, you can ignore it. Okay. Yes, Tanya, it's just a theoretical thing. Theta of n just means that it's bounded above and bounded below. Theta of n, like I said, you're saying that it's in the same class as linear functions. Its growth is not going to be faster than linear functions, and it's not going to be slower than linear functions. So it will be, that's a good question. It will be in the big theta notation if you can always put an upper bound and a lower bound on the time complexity. For these examples that we've done so far, we're talking about the worst case time complexity. In the worst case, you have 2n plus 2, which is an exact function that you know. When it's an exact function, you can put an upper bound on it and a lower bound as well, right? So when you can put both bounds, it's theta n. But if you can only put an upper bound and you don't know the lower bound, then you just talk about big O of n. Mostly in algorithmic design and research, what they are primarily concerned about is putting an upper bound, because that's how it matters in the worst case scenario. It's not fixed, no. It depends on what you can say about your algorithm. If you can mathematically analyze it and put both an upper bound and a lower bound, you can put big theta of n, but if you only find an upper bound, then only big O. What if we can't find upper and lower bound? That's mostly you're able to do if you, let's suppose if you're theoretically unable to find how many number of steps you're doing, you can do some simple rough mathematics. You just go through your algorithm and see how many steps it's counting, how many steps it's doing. In that way, you will know at worst if you see that let's suppose you go through the entire loop n times, then you can simply just go through your algorithm and count the number of steps that it's executing, and you can just get an upper bound. And if it's, let's say if it's your algorithm is a long algorithm and you don't want to go through the entire algorithm, what you can do is you can also graph the time it takes against the size of the input. So let's suppose you give me an algorithm that sorts my list. To do a rough analysis on the time it takes, I will just maybe I count the number of floating point operations or count the total number of steps, and I will graph it against the size of the input. So I will check, for example, let's suppose I take on the x-axis, so this is a rough analysis I will do where this is my where this is my size of input, and I will check how's the time increasing. So for example, if the time is increasing linearly, I get a rough idea that your algorithm that you've given me is perhaps theta of n or big O of n. If it's increasing like this, perhaps I can say it's theta log of n. If it's increasing exponentially or if it's increasing quadratically, then I can check. This gives me a rough idea of what kind of algorithm I'm dealing with based on how it's increasing, how the time is increasing based on the size of the input. So this is a rough analysis you can always perform to see what kind of upper bound and what kind of lower bound you can expect. Once you have this rough analysis, then you can try to mathematically prove it as well. But sir, we're not checking mathematically. Right now we are checking mathematically as far as these algorithms are concerned, because we've just put an exact number on it. So over here we put the number 2n plus 2. So for example, it's if n is size 5, you know that it's going to be 12 operations. Okay. So right now we are doing this mathematically. Okay, I'm going to ignore Jafar's question because it's irrelevant. Okay, so if we are all on board with this and there's no more question, let's move on to the binary search algorithm. Okay, so for the binary search algorithm, this is what we do. Let's consider a list of size 8. Okay, so how does binary search work? If you recall, what binary search does is the following. It takes a list, it sets I and j at the starting at the end of the list that is under consideration. It then finds the middle value. If I have the binary search algorithm lying somewhere so I can show it to you as well. Here we go. Let me just put this here, and here is your binary search algorithm. Remember that we put I at the start of the list, j at the end of the list, and we find the middle value and we do a comparison over here. So there's two comparisons happening. We are checking whether I is less than or equals to j, and we're also checking whether your current element is greater than or smaller than your middle element, right? So if you recall, this is something that we did. We were going through this list. This was the first element, this was the last element, and we were checking whether it was how it compared to the middle element. So if we look at the algorithm in detail, it's doing two things. The comparisons that are happening are like this. This is I is less than j, that's one comparison that's happening. And the second comparison that's happening is we're checking whether it's bigger than or smaller than the middle element. And so if we try to analyze it, this is what's happening. If you have a list of size 8, I will be set to this 1, j will be set to 8, and middle element will be the smaller you take a, because it's an even size list. So this will be the element. For convenience, I have picked a size that's a power of 2. So I have right now taken 2 to the power 3 as the size of my list, and I've done this because at every step your size of the list is going to become half of this. So if it was size 8, now it's going to become size 4, right? So let's suppose I checked and I realized that the element that I'm looking for has to be in this part of the list, this half. So I just consider this part I to m and ignore this. So I changes, j changes, and so this is my current list. Then let's suppose in the next step I realize that the element that I'm looking for has to be in this part. I consider these two and then ignore these two. And then finally, let's suppose this is the one that I'm looking for. I do another comparison. So this is how binary search works. For a size of 2 to the 3, it becomes a list of size 2 to the 2. Then it becomes a list of size 2 to the 1, and then finally it becomes a list of size 1, which is 2 to the power 0. Does that make sense? So in each stage you can consider what's happening. Each stage has different elements. So the first stage had 2 to the 3 elements. The second stage had 2 to the 2 elements, the third stage had 2 to the 1 elements, and the last stage had 2 to the 0 elements. And there were a total of 4 stages: first stage, second stage, third stage, and fourth stage. Alright? And so now we can generalize this. We can generalize by saying that if consider the following. Let's look at. So what was happening, you had 2 to the 3, 2 to the 2, 2 to the 1 and 2 to the 0. And if you think about 2 to the 3, if you think about k equals 3, then the number of stages that you had were 4. So the number of stages, so if your list size is 2 to the 3, the number of stages is 4, which is 3 plus 1. If your list, which is basically 3 plus 1. If your list size was, let's suppose 2 to the 4, if you had 16 elements in your list, then you would have had 5 stages, because 16, then 8, then 4, then 2, then 1. So 5 stages, which is simply 4 plus 1. And so the idea is, if you have 2 to the k elements in your list, then the number of stages will be k plus 1, where you can see simply that k is simply log base 2 of n, small n, not big N. Let me write this again. K is simply log base 2 n. If you take the log of this, you will get k, log to the base 2. Okay. So if n is equals to 2 to the k, then if you take log base 2 of n, you get log base 2 of 2 to the k, which is k times log base 2 of 2, which is simply k. Okay. When the elements are not in 2 to the n form, that's a good question. I will address this at the end of it, at the end of the discussion. It's easier to just talk about 2 to the n first, and then we'll talk about what happens when they're not in 2 to the n form. So let's just understand what's happening in 2 to the n form. Okay, so generally for a list of size 2k, each stage has 2 to the k minus 1 elements, with a total of k plus 1 stages. Okay. And so now it's very easy to see what are we doing with logs. We're expressing k in terms of n. We need logarithm to the base 2 to find what will k be in terms of n. If you have a list of size 2 to the 3, how do you find this 3 from this n? If you have n equals to 8, how do you find k? Well, k is simply log base 2 of 8, and you can check that this is simply equals to 3. So whatever n you have, you take log to the base 2 of that number. Is that clear, Daniel? Okay, and so let's see, now that we know how many stages we have, we simply need to check the operations that we're doing. And remember, we were just doing 2 comparisons in each stage. We were checking first was I less than j, and then we were checking whether x was greater than or smaller than this middle value. So 2 comparisons in this stage, 2 comparisons in this stage, 2 comparisons in this stage, and 2 comparisons in this stage. So if you have k plus 1 stages, you are doing 2 times k plus 1 operation. So the first operation is I is less than j, which was being done once in every stage, and the second operation was checking whether your elements that you're looking for is bigger than or smaller than the middle element, which you're doing once in every stage. There are k plus 1 stages, and so k plus 1 plus k plus 1 gives you 2k plus 2, and we've already expressed k in terms of n. So we have 2 times log n plus 2. And so again, you have a worst case time complexity of theta log n. Okay. So this is something interesting. We had linear search which had a worst case time complexity of theta n, but you have a binary search which has a worst case complexity of log n, and log n is a much smaller class than the linear class, which means the growth of this number is not going to be very large. So if you look at this graph, my linear search, the time taken for that linear search will increase linearly, but the time taken for my binary search will increase as a log function, which means after a large value of n, my binary search will be much faster it will take much less time than my linear search. Okay, so k was simply, we were trying to figure out, I expressed these numbers, this was 8, 4, 2, 1. Instead of thinking about them in terms of 8, 4, 2, 1, I thought of them as powers of 2. And this power is simply k. So this is 2 to the k, and then you're checking what's the value of k. So if you have n to be 8, how do you find k? How do you find what's the power? How do you solve an equation like this? This is a simple college algebra problem, which is that if you have an n to be equals to 2 times k, how do you find k? Find k. And you find k by just taking logs on both sides. And we used k to find a pattern, number of stages. When we use k, we see simply that if I express 8 as 2 to the k, 8 as 2 to the 3, then I will have 3 plus 1 stages. If I express 16 as 2 to the 4, I will have 4 plus 1 stages. So if I express my n to be 2 to the k, I will have k plus 1 stages. This gave me a good way to express how many stages I will have. Okay. All right. So the worst case time complexity is a logarithmic function, and so binary search is much faster than linear search. K is indicating number of stages. K plus 1 is equals to the number of stages. Okay. Again, if n is 2 to the k, then number of stages is k plus 1. All right. Okay, so now to address Jaffar's question, what if we have a list? Let's suppose we have a list of 10 elements. Instead of 8, we have 10 elements. So let's suppose A1, A2, A3, A4, A5, A6, A7, A8, A9 and A10. Let's suppose we had 10 elements instead of 8, and so now I can't express n as 2 to the k. Okay. Actually, let's just consider not 10 elements, let's consider A1 to A6, A3, A4, A5, A6. N is now 6, which is not a power of 2. And so let's consider what happens when I try to halve this. Let's see how many stages do we get. So for this one, if at this stage, first I will have 6 elements at the first stage. Then in the next stage, I will have 3 elements. Then in the next stage, I could have, let's suppose when I have 3 elements, I could either get this part of the list, or I could just get this one number. Let's take the worst case scenario. Let's say we get 2 elements in that list. So 6, 3, in the next stage we get 2 elements, and then finally we get 1 element. So if I had 6 stages, 6 elements, I still get maximum of 4 stages. Okay, and remember that even for 8 elements we got 4 stages. So instead of thinking about what kind of instead of worrying about this element, let's suppose I had 6 elements. If log of 6 is going to be 2 point something, right? It's not a nice number. Log of 6 is going to be 2 point something. If I floor this, then I get 2. And so when, after flooring this, you consider this to be k. And now instead of using k elements, think of a list. A list of size 6 can be expanded to a list of size 8. Let's suppose I had 6 elements, these 6 elements. If I just add 2 dummy elements over here, A7 and A8, then what I have is now a list that is of size 8. I have made it larger. Even though I went from 6 elements to 8 elements, my number of stages did not change. So whenever you have a size that is not a power of 2, you can go to the next power of 2. For example, if you take a size of 7, what's important is that you consider what different k's are. So for, let's suppose, let me write a size and number of stages. Let's suppose, and let's make this table k. If you consider k to be 1, then your size is of course 2 to the 1, and you have of course stages k plus 1, which is you have 2 stages. Then if you have k to be stages is k plus 1. If k is equals to 2, then size is 2 to the 2 and stages are 3. If k is 3, size is 2 to the 3, this is 2, this is 4, this is 8, and if you have size 8, then the stages that you have are 4. If you consider size 4, then that's k4, then that's 2 to the 4, which is 16. You will have 5 stages. Now the question is, what about the numbers in between? The numbers in between. For example, if your size is between 4 and 8, let's suppose when we considered 6, we still got 4 stages. So whenever you have a number that is between any of these numbers, you will expand your list to the next possible value of k. And the way we find out which k to consider is you take the log of this number and floor it. So first you find k, you get log of 6, log base 2 of 6, which is 2 point something. And then instead of using this, you will take the number of stages will be k plus 1. You will consider this, the next element. You will consider a list, of size 2 to the k plus 1. You will look at the next possible power of 2. So when it's 6, you're going to look at 8. When it's 7, you're still going to consider the next biggest one, because it can't be bigger than this. The number of stages will going to be 4 instead of 3. Now for example, let's suppose your list was of 10 elements. If n was 10, you are going to consider the next power of 2, which is 4. So you will consider if you find k to be as log of n, So let me bring out the notes which have them written nicely. If n is not a power of 2, we can add some dummy elements and expand the list to 2 to the k plus 1 elements. So instead of where k is floor of this, so we want to floor it and then add another 1 to this. So we floored it to get the previous one. The reason we floored it was to find the previous one. When you floor this, you get 2, and then you have to expand it to a list of 2 to the k plus 1. So which is, your size will be 2 to the 2 plus 1, which is 2 to the 3. And now if you think about it, the search would of course just require 2 to the ceiling of log n plus 2. So for example, my log n in this case was, if you consider, here it is, let me read this up. So the search would require 2 to the log n, which is a ceiling of this. Let's consider this in our example. So first we found k. N was 6. I found k to be floor of log base 2 of 6, which was 2. Then I know my list will be of size 2 to the k plus 1, which is 2 to the 3. So for 2 to the 3, I know that I'm looking at this list 2 to the 3. This is, and so the number of stages will be 4. So I know the number of stages is 4. And so the complexity, the number of operations we know, is 2 to the 2 times k plus 1. And so when I look at this, I know it's going to be 2 to the, I can write this next k. So if you consider k to be 2, this is basically, this is log, the floor of log n, and this is the ceiling of log n. When n is 6, this is the floor, 2 is the floor, and this is the ceiling. And so you can simply say that this number is 2 times the ceiling of log n plus 2. Does that make sense? Don't think of it, I think it's better if we don't think about it in terms of k at all. We can simply think about, if you find log n, then the floor of log n will be either this, will be this number, and the ceiling will be this number. And so you're interested in this list, and so you get 2 times the ceiling of log n plus 1. Let me know if that is clear so I can move on. There is an obvious change that has happened. Over here the meaning of k was something different. Over here the definition of k was something different. Instead of using k, we should just use a different variable. Let's call this, I don't know, L perhaps. L is equals to this, and consider a list of size L. Let's make this L, so this will become easier. Don't consider this to be k. This is L. This is L. Okay, cool. Everyone else, is this clear? If it is, I will move on to the next concept. Okay, great. So in the next one, what we have is the average case complexity. So far we were talking about the worst case complexity, which is what happens when your element is, let's suppose, at the end of the list, because then you can't find it in the middle. The average case complexity is different. The average case complexity is, on average, how many number of operations would you use over all possible inputs. So if you consider all different possible inputs, what's the average time complexity of your algorithm? And this is not easy to do for different kind. Worst case analysis is at least very easy to consider for simple algorithms, because you can make the worst case and you can talk about the worst case. But for average case, you don't need to consider one worst case. You need to consider all possible inputs, and that's not easy to do for different algorithms. It is easy to do for linear search, which is why we will do it, but it's not easy to do for other different kinds of algorithms. Yes, Jafar, do you have a question? Okay, until we wait for Jafar to tell us whether he has a question, let's move on. And so let's consider what happens in the linear search. In the linear search, you have different possible inputs. You are trying to find an element X in your list, and the possibility is X can be in different positions. If your list is of size n, if your list is of size n, let's suppose you have n elements, a1, a2 up until an, then this element could be X, or this element could be X, or the last element could be X. So there are these different n possibilities for X. Okay, and so X can be in the first position, X can be in the second position, or X can be in the last position. We've already discussed what happens if X is in the last position. If X is in the last position, you will have 2 times n plus 1 comparisons. But if you have total comparisons, if X was in the first position, you only need 3 comparisons. What are these 3 comparisons? These 3 comparisons are as follows. Let's suppose this was the first element. Then you are doing I is less than or equals to n. You are checking X is equals to an. And then after this was in the loop, and to exit this, you will immediately exit the loop because this condition will not be satisfied. And then you need to do one more comparison, I is less than n. So there will be a total of 3 comparisons. Let me bring up the linear search algorithm again, which was this one. So notice that you're going to do this once, you're going to do this once, you're immediately going to exit the loop, and you're going to do this one. So only 3 steps. Okay. And then if you think about what happens for different position, now let's suppose it wasn't in the first element, let's suppose it was in the second position. Oops. If it was in the second position, okay. If it was in the second position, then you're going to do this 5 times. You're going to do a total of 5 comparisons. And the reason is as follows. You will do this once, both of these. So these are 2 comparisons you're doing. Then again you will do 2 comparisons, which is 4. And then finally you will exit the loop because this condition is not satisfied. And you will exit the loop because this, and then do this comparison. So there's a total of 5 comparisons to be done when your X is in the second position. And so now let's consider the general case. If your X is in the first position, 3 comparisons. If your X is in the second position, 5 comparisons. If your X is in the nth position, you have 2n plus 1. And to do the average case complexity, you're going to add all of these comparisons for different possible inputs and average them over all of these. So the total number is, you find the average of all of these. So 3 plus 5 plus 7 plus blah 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 up until 2n plus 1 divided by n. And so the average becomes n plus 2. Let's check out the mathematics a bit. And so the mathematics is done as follows. So we have 3 plus 5 plus 7 plus up until 2n plus 1 divided by n. And now this can be written as, if I write this as 3 plus 5 plus 7, this can be written as An easier way to do this would be to write it as okay, so you can actually write this 3 as 2 plus 1. You can write this 5 as 4 plus 1. You can write this 7 as 6 plus 1, and so on. And the last element would be 2n plus 1. Okay. And so if first let's add up all of these ones. These are n terms. So you have n times 1, so we can just write an n for all of these ones. Okay. And the rest of the terms are 2 plus 4 plus 6 plus up until 2n divided by n. So I have just written 3 as 2 plus 1, 5 as 4 plus 1, 7 as 6 plus 1, 2n plus 1 was already in that form. And so then I just took out all the multiples of 2 and wrote them separately, and took out all of these ones which were n ones, which is just n. So 1 plus 1 plus 1 plus 1, you just get n because there are n terms. And so now you can write this list as 2 times 1 plus 2 plus 3 plus up until n. Take 2 common from all of these numbers and you get plus n whole divided by n. This is just nothing but the sum of the first n integers. We know that 1 plus 2 plus 3 up until n, the sum of first n consecutive integers is nothing but n times n plus 1 upon 2. We've derived this formula in the previous classes. And so now we can replace these by this. So note using this. And so I can rewrite this as 2 times n times n plus 1 upon 2, and I can write this plus n upon n separately, plus n upon n, and so this 2 and 2 gets cancelled out, and what you have, sorry, this was n, not 2, and so this was 2, and so this n and this n gets cancelled out, and what you have is 2 times n plus 1 plus and n again get cancelled 1, so this was just simply 2n plus 2 plus 1, and so this is still theta of n. Okay. Any confusion? I've gotten a different result. N plus 2, I've botched up the mathematics somewhere, and I'm not sure where I have botched it up. Let me just check what I've done wrong. Oh, I did miss a factor of 2 over here. there's a mistake here. Let me redo this computation. Okay, so replacing this by this, I get 2 times n times n plus 1 upon 2 plus n upon n. Yeah, this was the mistake. So cancel 2 and 2, and you get n times n plus 1, n times n plus 1 plus n divided by n, which can be written as n times n plus 1 divided by n plus n upon n. Separate these two addition terms like this, cancel out the n's, and you get n plus 1 plus 1, which is n plus 2. Yeah, that's the correct computation. So this tells us that even for all possible inputs, my average case complexity is theta n. I'll just go back to the notebook so that you can see the computation. Jafar, were you able to see the computation that you wanted to write down, or do you want me to go back to some previous page? Which one? Is this the page that you wanted to see? Okay. All right, so we can move on. Let's go back to the notes. Okay, let's talk about bubble sort now. Let's show you the bubble sort algorithm so that you can recall what the bubble sort algorithm used to do. Here is the bubble sort algorithm, and essentially it did the following. It would make passes, it would make total n minus 1 passes, and in each pass it will do the following. So in every I pass, in the ith pass, remember what we were doing? In the first pass it compared these two, and then it compared these two, and up until these last two elements. But in the second pass we were not going to check these two elements, we were going to start and stop at these two. So in terms of I and j, in the ith pass you do n minus I comparisons. What does that mean? So in the first pass you will do n minus 1 comparison. So first comparison, second, third, fourth, and fifth, where n was 6, so you are doing 6 minus 1, 5 comparisons. Then I is 2, you are doing the second pass, then you will do 6 minus 2, which is 4 comparisons, 1, 2, 3, 4. So in the ith pass you will do n minus I comparison, and the total number of passes is n minus 1. So for example, if you had a list of 6, elements, you will be doing a total of 5 passes, and in each ith pass you are doing n minus I comparisons, because you're doing whether these two are same and these two are same, and then you're interchanging them. And so this is how the mathematics works out. So in the first pass you were doing n minus 1 comparisons, in the second pass you were doing n minus 2, and then finally in the last pass you will be comparing just one element, right? So if you add these together, n minus 1 plus n minus 2 plus blah 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 up until 2 plus 1. And this is nothing but the sum of the first n minus 1 elements, which can simply be written as n minus 1 times n over 2. And so this is something interesting. Now you have the first example where your time complexity is actually quadratic. So the factor that you're getting, this is n square over 2 minus n over 2. This is theta n squared. So this is a quadratic algorithm. Okay? Is this clear to everyone? I starts from 0 or 1, depends on the algorithm, Jafar. Over here, if you recall the bubble sort algorithm, just look at the specific algorithm that you're talking about. In the bubble sort algorithm, I was starting from 1 to n minus 1. So this was the ith pass. And if you look at perhaps the linear search algorithm, I was starting from 1 and it was going till n. If you look at the maximum element algorithm, it was starting from 2 and going to n. So it depends on the algorithm, Jafar. Okay. So for the bubble sort, we have quadratic time. Now let's see if insertion sort is any better or worse than bubble sort. Okay, so what does the insertion sort algorithm do? The insertion sort algorithm, if I can bring it up here, remember what it did. When you have these two, it just compares these two and tries to plug in, think of this as the jth element. This was the second element and it was being found its correct place in this list. So it's going to place in the first position. Then you consider that this list is sorted and you're placing this element in the right position. Then let's suppose you're considering this list and you're placing this element in the right position. Now let's consider a jth element. So if j is 5, let's suppose 1, 2, 3, 4, 5, you're placing the fifth element in a list that is of size j minus 1. But to find its correct place, you are doing something that is like linear search. You're starting from the first element and you're seeing whether it can be placed here. So you're doing one comparison, then second comparison, then third comparison, first comparison, second comparison, third comparison, and fourth comparison. So you're doing, for every j element, you're doing for each jth element, you are doing a linear search on j minus 1 elements. Does that make sense? It's actually, insertion sort is using linear search over and over again. For example, for this element, it will go through this, it will go through this entire list. So actually insertion sort is doing linear search first over this, and then over this, and then over this, and then over this, and so on. So you're essentially using linear search a bunch of times. So we can talk about how it's doing that. It inserts the jth element into the correct position in j minus 1 elements. It uses linear search to find the correct position. And linear search, for each element, it's doing j comparisons to insert the jth element. So for example, if you were looking at the worst case scenario, for this element, you're going to compare with this one and this one and this one and this one, right? So for the jth element, you're doing j comparisons at max. And so then you can add these numbers up. So j starts from, you're essentially looking at this list where j will start from the second element. This was j, and it will go to up until the last element. So j goes from 2 to n. And so for the first element, you're doing 2 comparisons. For the second one, you're doing 3 and 4 and 5 up until n. To add all of these up, this is nothing but the sum of first n integers minus 1, because you don't have 1 here. So this is the sum of 1 to n, and then you just subtract 1. And now if you expand this, you see that even this is n squared upon 2 plus n upon 2 minus 1. So even the time complexity of insertion sort is quadratic. So even though it seemed that it should be faster, essentially, sorry, this was the, let me go through this again. So you're going through j comparisons to insert the jth element, 2 plus 3 plus 4 up until n, and when you add these up, you get n times n plus 1 over 2, because this is nothing but the sum of first n integers, but 1 is not here, so you subtract 1. And so this is a quadratic function. You can see the first factor is going to be n squared over 2, the second term is going to be n over 2, and the last is 1. So this is a quadratic function. And so this is big theta of n squared. So even bubble sort was n squared, and insertion sort is also n squared. And even though it seemed that insertion sort might be faster, the fact that it has to do a linear search n times makes it slower. And it's not slower, but it's of the same class, quadratic class, as the bubble sort algorithm. Let me know if that makes sense. If you have any questions, let me know. I'm going to pause for a couple of seconds. Again, the question is simple when the answer is simple. If you can do a mathematical analysis, this function is easy to see that it's quadratic. And for a quadratic function, you can always say that it's upper bounded by a quadratic function and lower bounded. When you can produce both bounds, upper and lower, then it's big theta. But if you can only find an upper bound, it's big O. And if you can only find the lower bound, it's big omega. Not much is left, Jafar. We have to do this matrix multiplication algorithm, and then we're just going to discuss some conceptual ideas. I see that there's something missing, but that's fine. We'll fix it. Anyway, if that's clear, let's just look at this matrix multiplication algorithm. Let's suppose you're multiplying two matrices. When you multiply two matrices, let's suppose the first is m by n and the second is n by k, you can actually think of this multiplication. Let's suppose you have an m by n matrix which is being multiplied by a n by k matrix. What you do for each element is notice that you do one row and multiply it by one column. So row into column is something that is being done. So if this was A11 and A12 up until A1n, and let's suppose this was B11, B21 up until Bn1, what you're going to do is multiply this with this and add them up. So you will get A11 times B11 plus A12 times B21 plus up until A1n to Bn1, and this will give you the element C11. And so this can actually be simplified to be written as the ij element is given by aij dot bj1 plus ai rad. Yeah, ai, hold on. Yeah, aij plus bj1. So if you are considering this one, column goes from 1 to, sorry. So let's suppose Ci1 you're looking at aij is actually ai1 times b1j plus ai2 b2j up until ain bnj. Okay, so this is the multiplication that you do for matrix multiplication. You multiply a row by a column of the matrix, and there is a simple algorithm that you can write down, which is given here, that you have A to be an m by n matrix, B to be an n by k matrix. You start your first loop by going from 1 to m. You start your second loop by going from 1 to n. So these are the rows of m, these are the columns of A. Sorry, these are the rows of A and these are the columns of A. And to find the Cij element, you're going to do k multiplications and additions. So on every step, you first notice that the element is being written as 0, and then you keep adding. You take the first multiplication and add it. Then you do the second multiplication and then add it. So what's being done is, first Cij is set to 0, and then you added A, I1, B1j, and then you add them all up. So first you add this term, then this term, and this term, and so on. And so this is written in this form. This is the algorithm. We did not cover matrix multiplication algorithm. I'm introducing it right now. You all know how matrix multiplication is done, and the algorithm is very simple to understand. Okay, and so consider that these are m steps being done, then n steps being done. This loop will be run m times, this loop will be run n times, and then this loop will be run k times. So if you ask the question, if A and B were the same size, if A was an n by n matrix and B was an n by n matrix, so if you want to make a matrix C which has n by n matrix, it will have n square entries, and let's see how many operations you will need to do. You will be doing some multiplications and you will be doing some additions. The total number of multiplications that you will do is, for each element, since there are n square entries, you are doing n plus n multiplications, and additions are n minus 1. So the way this will work for a matrix of size n by n is that if you've managed to make C, which is an n by n, notice there are n square entries, and for each entry you are doing this process. You are doing this algorithm n times. So Cij is made by doing 0 plus ai1 b1j plus so on. So you're doing n multiplications for each entry and n minus 1 additions, because 0 plus this is not an addition, the additions are n minus 1. So n minus 1 additions for each of the n square entries. So the total multiplications will be n square times n, and the total additions will be n square times, so total multiplications is n square times n, and the total additions are n square times n minus 1. And if you add them up, you get n cubed plus n cubed minus n squared. I'm just adding this term, and the total is 2n cubed minus n squared. So matrix multiplication is actually big theta of n cube. This is the first cubic algorithm that we are seeing. If you want to multiply two matrices, you will need n cube operations if they are both, if A is n by n and B is n by n. You will need big theta of n cube operations. Let me know if that makes sense. So you have 2n cube minus n squared operations. Notice that over here we're not doing any comparisons. We are looking at multiplications and additions. And these are called floating point operations for your computational numerics. Does this make sense? Okay, just gonna wait for other people to let me know if this is clear. Okay. So we've talked about different complexities today. We found some algorithms were log n, some were linear, and this is the increasing they're written in increasing order of complexity. You have constant complexity if your function does only, if your algorithm just takes constant number of times for every input. So if you have an algorithm that makes 5 steps for every size of input that you give it, then it's a constant complexity algorithm. If you have something that increases as the log of your input size, then that's a logarithmic complexity algorithm, or the algorithm can have a linear complexity if it's theta n. It can have a linear rhythmic complexity, which is worse than linear but better than quadratic. So n log n is slower than this but faster than n squared. So if you can make an algorithm which is, let's suppose you were trying to make an algorithm faster than a quadratic, even if you're unable to make a linear complexity algorithm, if you're able to make a linear rhythmic time algorithm, that's still faster than a quadratic polynomial. So after n log n you get n squared, after n squared you can have n squared log n, and so n to the b are polynomial complexity, then exponential complexity, and then factorial complexity. Okay, and so up until polynomial time complexity, we say that they are manageable, they are tractable, you can solve these algorithms. But if your algorithm takes worse than, if your polynomial complexity is very high, let's suppose it takes n to the power 10 or n to the power 100 polynomial time to do your algorithm, then it's very slow. Or if it's exponential, then it's very slow, then those algorithms can't be solved in a reasonable amount of time for a large input. So let's suppose if it's n to the power 100, and if you give it a size 1000 algorithm, it's going to, if size 1000 input, it's going to take way too long to solve your problem. And that's way too slow for, so up until polynomial complexity, I say n squared or n cube, it's still doable for small size or even large size problems, but after that it's very slow. So up until here we draw the line that after polynomial complexity, exponential complexity is just ridiculous and not doable. Okay. There's a concept of algorithmic paradigm, which is some algorithms can look very similar. So maybe they're for different problems, but the concept behind them is the same. So for example, the brute force paradigm is to check every possible input. Let's suppose you're trying to crack a password, and if your approach to crack a password is to guess every digit and try out every possibility for the digit, then you're running a brute force algorithm on it. And so the brute force algorithm just checks every possible input and tries it and see if it works or not. Okay. And so for example, if you were linear search is sort of a brute force algorithm where you check every element and you see whether it's same as your element or not. Then there is another different kind which is called greedy algorithms, the kind of algorithm that we did for task scheduling and the cashier's algorithm. Those were both greedy algorithms. So they're in the same paradigm. They're not the same algorithm, but their approach to solving the problem is the same. Similarly, divide and conquer means, for example, binary search was a divide and conquer where you half the list at every stage. Similarly, there's a sorting algorithm called merge sort, which uses the divide and conquer, which is you sort half the list first and then you look at the rest of the list. So at every stage you're breaking down your sorting into halves, your list into half and half, and that's called divide and conquer. You have another paradigm called probabilistic algorithm, if you see. So the concept over here is different algorithms can have the same approach, even if they are for different problems. Okay. And there is something missing over here which I will just bring up. So we have the idea, so we call problems which are polynomially solved, they're called tractable because you can solve them in a reasonable amount of time. And so there's also a question about P versus NP problems, which are P problems are problems which can be solved in polynomial time. NP problems it's short for non-deterministic polynomial, which is we don't know if there exists a polynomial time algorithm for NP problems. No one has found any. So if your problem is NP, it means nobody has found a polynomial time algorithm to solve that problem. There's also an important thing about NP problems. NP, there doesn't exist a polynomial algorithm for it, but it can be checked in polynomial time. So for example, if somebody claims that they have a solution to an NP problem, you can immediately check it in polynomial time. For example, this is something that we have done in detail. Consider the problem of finding the truth value. Let's suppose you have a compound proposition. Something like P, Q, and or R negation implies P or Q negation and R. Now, this is a compound proposition. I can add perhaps an S to it as well. I could add a T to it. And this compound proposition contains P, Q, R, S, T. And consider the problem question, is there any combination of the truth values of P, Q, R, S, T that makes the compound proposition true? So the question is, is there any combination of truth values of P, Q, R, S, T which I can set over here so that this entire proposition is true. Now, obviously, if you have 5, then you know that there are 2 to the 5 possibilities. This can be true and false, this can be true and false, this can be true and false. And so there are 2 to the 5 possibilities. And so if your algorithm is just to make a truth table, if you're trying to make a truth table, that truth table will have 2 to the 5 rows, which means you have, if you have n elementary propositions, if you have n elementary propositions p, q, p1, p2 up until pn, then you will have to check 2 to the n rows of your truth table. Your truth table will be of size 2 to the n. And so your algorithm is actually an exponential time algorithm. And so this is an NP problem because we don't have a polynomial time algorithm to solve this problem. However, the important thing is that if somebody states that, let's suppose the solution is P1 is true, P2 is false, P3 is true. For example, in our example, if somebody says that the correct solution is P is true, Q is false, R is true, S is false, and T is false, okay? Let's put T here. Then I can immediately put the values here and check it. And you can check it in a very short time. You can check it in polynomial time. So NP problem have 2 characteristics. You can't solve it in polynomial time, but you can check it in polynomial time. And to check this, you just need to insert the values and see if it's a solution or not. And that is the end of the lecture for today. Let me know if all of this discussion was clear to you and if you have any queries or not. Okay. Great. That's it for today. P versus NP. Okay. Let's go back to this. P versus NP is simply, it's a class of algorithms. You have different problems and different problems are in different classes. If your algorithm is a polynomial time algorithm, we say it is in class P, that is, there exists an algorithm that can solve it in polynomial time. If you don't have a polynomial time algorithm for your problem, and there are many problems for which polynomial time algorithms don't even exist, then those are in NP class, non-deterministic polynomial, because you don't have a polynomial time algorithm that can solve it. And polynomial time is good because it's a reasonable amount of time for even large number of inputs, a large size input. Does that make sense? Okay, great. Let me know if there are any other questions. I'll stay online for a few minutes and then I'll end the stream. with the ceiling function formula. Okay. So the idea with the ceiling function was as follows. Basically, when it's in decimal, we're basically saying that if it's in decimal, we don't need to think about decimals. So let's suppose if I can bring that. Let me find the log. Okay, and so the idea was this, that if it's not exactly a power of 2, when you take the log, it will be in decimals. So for example, log 6 by Subhan, if it's log 6, it will be 2 point something. But the idea was we don't need to worry about it. If your input size is between 4 and 8, if it's not a power of 2, then you can find the log and you can seal and floor it to find the previous and the next class. The previous is set as L and the next is set as L plus 1. So this is L. What we basically do is we say that this was my L and this was my L plus 1. And so what's important is that we look into this class. So if this was L plus 1 class, then it will be 2 times the complexity will be L plus 1 plus 1. So we do ceiling and floor so that when you are in the middle of these classes, you can go into the next class. Ceiling is being done to find the next one that is important, right? So when we had a list of 6 elements, I expanded it to a list of, number of stages. So when you have a list of 6 elements, you still have 4 stages, right? And so if I remember, here we go. So for 6 elements, you want to go into the next class. So this was basically 2 to the 2 point something, and we seal it so that we get 2 to the power 3. So if you seal this 2 point something, you will get 2 to the power 3. So what you want is you basically want to go to the next class. Flooring and adding 1 is the same as sealing. So seal of x is simply floor of x plus 1. It's the same thing. You're absolutely right. Yeah. Yeah. So maybe if you think about this as k, then this was k plus 1. So if you found this to be L, where L was the floor of this, then you're doing ceiling is simply L plus 1, right? So what you can just write this as 2 into L plus 1 plus 2, which is nothing but the ceiling of log n plus 2. We did floor to find L and then we added L plus 1. Actually, let me just write this down in something different. So here's what we did. You do if n was 6, you do floor of log to 6 to get 2, and this is set to be L, and the class that you're interested in is L plus 1, which of course can be written as the ceiling of log to 6. So the complexity, the comparisons that you're doing are equals to 2 times L plus 1 plus 1 plus 1. Basically this was 2 times k plus 1, and k was your L plus 1 class. So this was 2 times L plus 1 plus 1, and n plus 1 is nothing but the ceiling. So 2 times ceiling log 2x plus 1. So if you can write it as L plus 1, do that. If you want to write it as ceiling, write that. Yes, this computes the number of stages. So L plus 1 is the number of stages. So you can set k to be equals to L plus 1. Actually, if you think about it, you don't even need to floor it, just seal it. If you seal log 2x to 6, you will just get the k stages. But it was explained in terms of flooring and sealing in terms of in your book, so I just went with this same terminology. Okay, perfect, great. No more questions? Okay, no problem. Do you want these notes that I was making as well, or are the uploaded notes good enough? If you want me to add these notes, then I can put these notes that I was making during the class as well. No problem. Bye, Hamad. What was so this was the first page. This is matrix, which was at the end. Size k, blah, 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 n equals to 2 to the k. This in search. Sure, I will add them. Okay, I will do that. Page 1, page 3, page 5, and page 7. Okay, thank you everyone. Have a good day. Bye. 3, 5, 7.